So far in this section, we have defined a path vector, a minimal path vector, and a minimal cut set. We're now about to define the analogous vectors and sets with respect to cut vectors, minimal cut vectors, and minimal cut sets. So starting off with a definition, a system state vector x is a cut vector for a coherent system if phi of x equals 0. And phi of x equals 0 corresponds to a failed system. So on the notes here, a path vector is a system state vector that corresponds to a functioning system. A cut vector is a system state vector that corresponds to a failed system. And if you add up the number of path vectors plus the number of cut vectors, you're always going to get 2 to the n power, where n is the number of components in the system. Here's another definition. A cut vector x is a minimal cut vector for a coherent system if phi of y equals 1 for all y greater than x. Now this goes back to our definition of inequality for vectors. And what's going on here with a minimal cut vector is, first of all, it corresponds to a failed system. But in addition, if you repair any component in that failed system, the system will go from failed to operating. So the intuition here is a minimal cut vector is a cut vector that is on the edge, in the sense that if any of the failed components get repaired, then that will bring the system back to a functioning state. Here's an example. We would like to find the cut vectors and minimal cut vectors for that very same system that we worked with before. In this particular case, you have 5 cut vectors, and there are the 5 of them. All 5 of those vectors correspond to a failed system. The next step is to try to figure out which of those 5 are minimal cut vectors. Well, it turns out the last 2 of them happen to be minimal cut vectors, and there they are. Okay, so let's look at the first minimal cut vector, 0, 1, 1. This component is down, this one is up, and this one is up. Well, what's going on there? In that particular case, if you repair any failed item, and there's only one failed component there, and it is component 1, if you were to repair it, the system would be up. The same is true of 1, 0, 0. This time you have component 1 operating, but component 2 and 3 are down. Well, if you repair any failed component, that is, fail either component 2 or component 3, then the system is restored. Here is the definition of a minimal cut set. It is the set of all indices I such that xi equals 0, and that is a minimal cut set corresponding to the failed components in the associated minimal cut vector. Now you remember in the previous definition for a minimal path set, we had the word functioning there. This time you're looking for the indices of the failed components. So for this first minimal cut vector, this one right here, where is the failed component? The failed component is in position 1, so component 1 alone is the first minimal cut set. And then for this vector right here, this minimal cut vector, the 2 failed components show up in positions 2 and 3, so those indices, 2 and 3, are your second cut set. The way you look at a reliability block diagram and figure this out, you simply say, look, if I draw a line in this fashion and say if component 1 is out, then this system is down. Likewise, for the second minimal cut set, if components 2 and 3 are out, I know that this system is down. In general, we denote these cut sets for a coherent system of n components by C1, C2, up to C sub k. Here's an exercise. Find the minimal path sets and the minimal cut sets for the bridge system, which we encountered earlier. Well, for the minimal path sets, we'll start with P1 here. One path through this system is through components 1 and 4. So that is one minimal path set. A second minimal path set is, and I won't draw this on here because this will get too cluttered, but if you start on the left and you go through component 1 and then through component 3 and then through component 5, that is also a minimal path set. But there are other path sets. For example, if you start on the left and you go through component 2 and then through component 3 and finally component 4, that is also a minimal path set. Finally, the last one, this one I can draw, we'll just keep it on the outside here. If you pass through 2 and 5 and they are both operating, that says that is our last minimal path set. We've got them all. Now, in addition to the minimal path sets, we want to find the minimal cut sets, so those get labeled C1, C2, etc. Here's the first one. The first minimal cut set is right here. If I know that components 1 and 2 are both failed, then the system is not operating. What is another minimal cut set? Well, if I go through these three right here, if those three have all failed, there is no path through the system. So 1, 3, and 5 is a second minimal cut set, but there are more. C3, if I draw this line right here through 2, 3, and 4, if 2, 3, and 4 are all down, it doesn't matter what state 1 and 5 are in, the system is definitely down. So 2, 3, and 4 is a minimal cut set. And by the way, there's no problem that P3 is 2, 3, 4, and C3 also happens to be 2, 3, 4. That's not a problem. And there is one last cut set in here, C4. And if you look at these components, you can see if 4 and 5 are out, doesn't matter what components 1, 2, and 3 are doing. That's definitely a situation in which the system is down. So there are the S equals 4 minimal path sets and the K equals 4 minimal cut sets for the bridge system. So at this point, we have established 4 different ways that we can specify the arrangement of binary components to form a coherent system. The first is to draw a reliability block diagram. The second way is to write out a structure function phi of x, where boldface x there is the state of the components x1, x2 through xn. The third is to specify the minimal path sets, P1, P2 up to P sub s. And the fourth way to specify the arrangement of binary components to form a coherent system are to specify the minimal cut sets C1, C2 up to C sub k. If you specify any one of those methods for specifying the arrangement, that implies knowledge of the other three. Now, one of the side benefits of doing minimal path sets and minimal cut sets is it allows us to write a coherent system as the parallel arrangement of series subsystems, or write any coherent system as the series arrangement of parallel subsystems, and that is what we'll do next.